Hello everyone, this is Chinnaiah Kalpana here. In this video, we're going to solve a differential equation. So let's get going. Problem: solve x plus 1 whole cube into y double dash plus 3 times x plus 1 whole square into y dash plus x plus 1 into y equal to 6 times log of x plus 1. So we are going to reduce the given differential equation into Legender's form. The Legender's equation is ax plus b whole power n into d power n y by dx power n plus p1 into ax plus b power n minus 1 into d power n minus 1 y by dx power n minus 1 plus so on plus pn equal to some function, that is some function of x. Okay, so if the equation is of this form, then we can call the equation as Legender's equation. But while comparing these two, we have x plus 1 x plus 1 in each term. Okay, that is an extra x plus 1 in each term. So what we'll do is we'll just reduce this equation to exactly, Legender's equation. Okay, we'll just take x plus 1 common from all the three terms of LHS so that the given equation will be reduced to Legender's equation. Let's see that. Given differential equation, x plus 1 whole cube into y double dash plus 3 times x plus 1 whole square y dash plus x plus 1 into y equal to 6 log of x plus 1. Consider it as equation number 1. Okay, now I'll take x plus 1 common from all these terms. We'll get x plus 1 into x plus 1 square y double dash plus 3 times x plus 1 into y plus y equal to 6 log of x plus 1, right? Now let's take this x plus 1 to RHS, then we'll get x plus 1 whole square into y double dash plus 3 times x plus 1 into y, sorry it's y dash, right? Y dash plus y equal to 6 log of x plus 1 by x plus 1. Here y double dash is nothing but d square y by dx square. Into x plus 1, y dash is nothing but dy by dx plus y equal to the RHS path 6 log of x plus 1 by x plus 1, right? So this is a Legender's equation form, right? So we are given a differential equation, we have reduced it to Legender's equation. Now we'll solve this Legender's equation by reducing it to a linear differential equation with constant coefficients by using some substitution. Okay, consider this equation as equation 2. See, we have equation 2, right? Let's replace d by dx by differential operator d, then this becomes, that is equation 2 becomes x plus 1 whole square into d square y plus 3 times x plus 1 into dy plus y equal to 6 log of x plus 1 by x plus 1, right? Now let's take y common from all the three terms of LHS, then we'll get x plus 1 whole square d square plus 3 times x plus 1 into d plus 1 into y equal to 6 log of x plus 1 by x plus 1. Instead of considering this equation as 2, we can consider the last equation, which is in operator form, as equation 2 for our convenience. Okay, don't consider this equation as equation 2. Let's consider the final equation, that is the equation in differential operator, as equation 2. Fine. Otherwise, you can just consider it as equation 2 and the equation differential form, operator form, as equation 3. Fine. Now we'll reduce this differential equation to a differential equation, that is linear equation with constant coefficients, by making some substitution. Let's see that. From Legender's equation procedure, we have a plus, that is ax plus b, can be replaced by e power z, then z equal to log of ax plus b, and theta is a differential operator whose independent variable is z, and ax plus b into d can be replaced by coefficient of x a into, since you're having power 1, right, so you'll have only one term of theta, say theta. And while coming to ax plus b whole square into d square, since you're having square, so you'll have two terms of theta, that is theta into theta minus 1 into a square, that is coefficient of x whole square. You'll get a square into theta of theta minus 1. Likewise, when you have cube, you can replace this by a cube into theta of theta minus 1 into theta minus 2. Since you are having cube, so you'll have three terms of theta. Fine. Now coming to our problem, let x plus 1 equal to e power z, then z equal to log of x plus 1, right, and here also theta is a differential operator whose independent variable is z, and here we'll replace x plus 1 into d by coefficient of x1 into, here we are having power 1, right, so you'll have only one term of theta, that is theta into 1, which is theta. Likewise, x plus 1 whole square into d square can be replaced by coefficient of x 1 square into, here you're having square, right, so you'll have two terms of theta, theta into theta minus 1, which gives us theta into theta minus 1, right. Now equation 3 becomes replace x plus 1 whole square into d square by theta of theta minus 1 plus 3 times replace x plus 1 into d by theta plus 1 into y equal to 6 log of, replace x plus 1 by e power z, you'll get log, okay fine, log of x plus 1 can be replaced by z, right, so you'll get z, 6z by, replace x plus 1 by e power z, you'll get by e power z. Now we'll just simplify this equation. This equation becomes theta into theta, theta square minus theta into 1 theta plus 3 theta plus 1 into y equal to 6z into 1 by e power z, right, we have written this fraction as 6z into 1 by e power z. Fine. Now we'll get minus theta plus 3 theta is plus 2 theta plus 1 into y equal to 6z into reciprocal of e power z is e power minus z, which is in operator form theta, right. This is of f of theta into y equal to some function of z. I'll call the RHS part as r, where f of theta is theta square plus 2 theta plus 1 and r is 6z e power minus z. Consider it as equation number 4, which is in operator form. So we have reduced the given, the equation 3, the Legender's equation to a linear equation with constant coefficients, right. Now we'll find the general solution to this equation 4, which results in terms of z, and using the solution of this equation we'll find the general solution to the given differential equation, which results in x, which results in terms of x. Okay, so this general solution to this equation is given by y equal to yc plus yp, where yc is a complementary function, yp is a particular integral. We'll find yc using auxiliary equation, and we'll find yp using 1 by f of theta into the RHS part of the reduced equation, that is the linear differential equation with constant coefficients. Okay, now coming to auxiliary equation to find yc, and later we'll go for yp. the auxiliary equation is f of m equal to 0, where f of m equal to, see we have f of theta equal to theta square plus 2 theta plus 1, right? Let's replace theta by m in f of theta, so that we will get f of m equal to m square plus 2m plus 1. Then the auxiliary equation becomes m square plus 2m plus 1 equal to 0, right? Which is an expansion of m plus 1 whole square. Okay. Now we'll write m plus 1 whole square as m plus 1 into m plus 1. Right. Now equate each factor to 0, we'll get an m plus 1 equal to 0, m equal to minus 1. Since m plus 1 is repeating twice, so you'll have m equal to minus 1, which are real and equal roots. Therefore, the roots are real and equal. So we got roots to the auxiliary equation. Now we need to find yc using these roots. We know that when two roots are real and equal, say m1 equal to m2, then yc will be one constant plus another constant into z. Here z is an independent variable, so we are using z. See, here z is our variable, right? So we'll use z instead of x into e power that equal root into z. Now coming to our complementary function, our complementary function will be yc equal to c1 plus c2z into e power that equal root, say minus 1 into z. From this we'll get yc equal to c1 plus c2z into e power minus z. Okay, now we got yc. Therefore yc equal to c1 plus c2z into e power minus z, right? Now we need to find yp, particular integral. Yp is given by 1 by f of theta into RHS part of equation 4. Is equals to 1 by f of theta is theta square plus 2 theta plus 1 into r, 6z e power minus z. We can write this as 6 1 by theta square plus 2 theta plus 1 into function of z, right? See, this is of 1 by f of theta into e power az into v form. So we'll solve this by shifting e power z towards left by replacing this theta by theta plus a. Okay, and later we'll operate a v using 1 by f of theta plus a, right? Just by comparing these two, we have a equal to minus 1, right? So we'll shift e power minus z towards left by replacing f of theta by f of theta plus a. Here theta plus a is theta minus 1. So we need to find, or we need to replace the f of theta by f of theta minus 1. Okay, if f of theta is theta square plus 2 theta plus 1, then f of theta minus 1 will be theta minus 1 whole square plus 2 times theta minus 1 plus 1, right? Let's shift e power minus z towards left just by replacing theta by theta minus 1. Then we'll get theta minus 1 whole square plus 2 times theta minus 1 plus 1 into this z. Okay. Then yp equal to 6 e power minus z into 1 by, let's simplify this denominator, expand theta minus 1 whole square, we'll get theta square plus 1 minus 2 theta plus 2 into theta 2 theta minus into plus minus 2 into 1 is 2 plus 1 into z. This gives us 6 e power minus z into 1 by theta square 1 plus 1 plus 2 minus 2 theta plus 2 theta gets cancelled minus 2 into z. Here plus 2 minus 2 gets cancelled, you will get 6 e power minus z into 1 by theta square into z, right? here we need to operate z by 1 by theta square. So I'll split 1 by theta square as 1 by theta into 1 by theta. Right? This gives us 6 e power minus z into 1 by theta into, if theta is a differential operator, 1 by theta will be integral operator. So here we need to find integral of dz is equals to 6 e power minus z into 1 by theta into integral z dz is z square by 2. Then yp becomes 6 e power minus z into 1 by theta into, you can write z square by 2 as 1 by 2 into z square. So here 1 by 2 is constant, so let's take it out. We'll get 6 by 2 into e power minus z into 1 by theta z square. Since 1 by theta is integral operator, so you'll get, or you can write this as integral z square dz, right? Integral z square dz is z cube by 3. Where 3 gets cancelled, you will get e power minus z into z cube or z cube e power minus z. Therefore, yp equal to z cube e power minus z. So we got yp and yc. Let's now find the general solution to equation 4, which is given by y equal to yc plus yp. Therefore, the general solution to equation 4 is given by y equal to yc plus yb. Then y equal to yc c1 plus c2z e power minus z plus yp z cube e power minus z, right? So this is the general solution to equation 4. Now using this solution, we'll find the general solution to the given equation. See, the general solution to equation 4 is in terms of z, as I said you earlier. Therefore, y equal to c1 plus c2z into e power minus z plus z cube e power minus z is the general solution to the differential equation 4. Fine. We have y equal to c1 plus c2z into e power minus z plus z cube e power minus z, right? Now, in order to find the general solution to equation 1, I'll use this, right? So, we can write e power minus z as e power z power minus 1. So that it will be easy to replace e power z by x plus 1, since x plus 1 equal to e power z, right? And z equal to log of x plus 1. Then y equal to this becomes c1 plus c2 z log of x plus 1 into e power z can be replaced by x plus 1. You'll get x plus 1 inverse plus z cube log of x plus 1 whole cube into e power z inverse. E power z can be replaced by x plus 1. So you'll get x plus 1 inverse. Okay, which is the general solution to the required equation. Therefore, y equal to c1 plus c2 log of x plus 1 into x plus 1 inverse plus log of x plus 1 whole cube into x plus 1 inverse is the required solution, which completes the problem. Well, we have seen a problem from Legender's equation in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.